Actually, if you're not good, then I'm not good. So, okay, so today's lab is dedicated to models. A lot of what we've talked about all semester kind of gets combined in today's work. We're going to be working with the atmospheric carbon model, which relates to global temperature. So throughout the lab, we've worked with seawater density and determining chlorinity, salinity. Today, what we're going to focus on is how these models are built and what good they're for, or why we use them, basically. Okay, so a model, in case you are not aware, and it's used in various disciplines. So whatever you're into, social sciences, political sciences, and especially in science and engineering, they're very useful. It's a representation of the real world. So for example, a model airplane is a representation of a real airplane. The problem with models is they're always flawed because they're always shortening things down. The best models we have are the ones that include the most detail. For example, a model airplane would be most like a regular model if you had a proportionate weight of gasoline and included all the different components. And a lot of times that gets really difficult to do, both in that example and in real life. It gets difficult to add in everything. This is a model of global temperature over time. It has two trends in it. One trend generated by a model is the dash trend. Doesn't include the effect of sulfate aerosols. The other trend line does. And the actual data, see, follows the trend lines with the sulfate aerosols much more faithfully than the other trend does. So we can see that the model with the sulfate aerosols captures more of what really happens in the atmosphere. And if you were to use a model to predict future climate based on greenhouse gases and sulfate aerosols, you would want to use the second model because it's more reliable. So they are very useful in determining future events and looking back in the past. Models are based on some kind of currency. So for example, this model is based on, let me give you another example. This is in your book, solar radiation model. And you don't have to worry about the details. The currency in this model is atmospheric or solar input, solar radiation. A lot of models work with carbon, like what we're going to be doing later today. So the currency for that model is carbon. So when you hear the term currency, you're thinking what you're measuring in different reservoirs and different fluxes. Now, so let me define the different terms that we use today. Okay, so first term is a reservoir. A good example of a reservoir is a reservoir. So one I always use too. So you could just think of your local reservoir. I'll draw it here. What affects the water level? Now, the currency for this model I'm going to do right here is water. What affects the water level? Well, rain, for example. What else? What's that?
Evaporation.
Evaporation, exactly. And you also have some inputs from groundwater or rivers and outputs from maybe pipes taking water out of it or irrigation. These different inputs and outputs, when they add up, now for example, if you look at your reservoir and find that your reservoir stays at the same level over a long time, it's what's called steady state. That means the inputs are equal to the outputs. When a model is at steady state, there's a useful calculation that we could do called residence time. Okay, residence time, well, one way to look at it is, now let's come back to a more realistic example, or something that you deal with every day. I looked these numbers up, I'm just kind of estimating them, but the current, does anyone know how many undergraduate students are at UGA?
37.
Well, that's total.
Oh.
25, okay? So the undergraduate class is 25,000. Okay? I just checked these out yesterday, so I guess they're fairly accurate, at least for based on last year. Now, every year, the freshman class inputs about 5,000 students. So 5,000 students are added per year. Now, we could assume that the population of undergraduate students at UGA is at steady state, meaning it's relatively 25,000 throughout time. That's a fairly good assumption. I mean, although in real world it's slightly growing, and some years it might